Okay, so now that we've looked at the linear discriminants, let's now use that idea to continue with the perceptrons. Perceptrons were single layer neural networks, really early ideas of neural networks. So single layer networks with threshold units. So if the input is greater than the threshold, then it fires a 1. So it was studied by Frank Rosenblatt in 1962, and they also built hardware implementations. So we can do binary classification with it. At about the same time, Widrow and colleagues were doing similar kinds of things with a thing called Adeline, which is adaptive linear elements. But we're going to look at perceptrons. So going back to our linear discriminant, we remember it looks like this. We multiply the weights times the x vector, and if the values are less than 0, we're going to classify as -1. If the value is greater than or equal to 0, then we're going to classify it as +1. So in here, where one class is defined as a -1 and the other with the +1. So just like we saw before, we're going to use gradient descent to train the perceptron. But Rosenblatt thought of quite a clever way of doing it. And we're going to minimize something called the perceptron criterion, which is essentially the error on the patterns. So remember that we have each input pattern has a target value t, and that is either +1 or -1, depending on which class it's. Apologies, I got cut off then. It's either +1 or -1, depending on which class it belongs to. So we get this. So if the pattern happened to be in the +1 class, i.e. when t is +1, then we know that if we multiply the weights times the extended weight vector times the extended x vector, it'll be greater than 0. And for patterns in the -1 class, i.e. where the t is equal to -1, if we multiply the weights in the x vector, we get less than 0. That means, because we use the +1 and the -1, we can do a bit of a tricky thing. It means that if it's been correctly classified, then it's always the case that if we multiply the weights times the x vector times the t, either the +1 or the -1, then that will be positive. It's positive in any case for the +1s, but in the negative case, the -1 flips it around. So it's always going to be the case that w times the x times the t is going to be greater than 0. So the perceptron criterion is defined as the perceptron criteria on the weight vector is summed over all of the misclassified patterns, and that w, x, and t, and minus because they will be negative, so that will make it positive. And if we add that all up, that's essentially the number of misclassifications on using the current weights. So we use this idea to do a perceptron training algorithm. So the idea is we cycle through all of the patterns in the training set, and then we test each pattern in turn with the current set of weights. So if the pattern's classified correctly, then we don't do anything. But if the pattern is misclassified, then we're going to add the pattern vector multiplied by eta to the weight vector if it's in the -1, if it's in the +1 class, or subtract it if it's in the -1 class. So this is going to change the weights in slightly the right direction to move towards the right answer. And we keep on doing that many, many times until it converges. So what Rosenblatt found was this algorithm's guaranteed to find the correct weight vector in a finite number of steps if the problem is linearly separable. So if it's like and or then and it's linearly separable, then the perceptron training algorithm will be guaranteed to converge eventually. The problem is, if it isn't linearly separable, the algorithm never terminates, so it runs forever. So the limitations of the perceptrons are that if the problem isn't linearly separable, the algorithm doesn't stop. That means perceptrons can't learn problems that aren't linearly separable. Essentially, it's flipping it from, it's making one misclassification on one side, and then it will go to the other side, and it sort of flip-flops. So perceptrons can't learn problems that aren't linearly separable. The problem is that almost all interesting problems are not linearly separable. And as I mentioned earlier, Marvin Minsky and Seymour Papert wrote this famous book called Perceptrons in 1969 showing that. And this is said to have ushered in the first AI winter, where a lot of funding dried up. It was known, however, that if you use a function of x in the dot product, it's possible to classify non-linearly separable problems, i.e. instead of if you use the dot product of x and the weights, you use a function of x with the weights, then you can classify non-linearly separable problems. The problem is that no one really knew how to train them for a particular training set. So we're in our AI winter, and we sort of know that if you use multi-layer perceptrons, so multiple layers of weights, you can solve this problem. The problem is no one knew how to set the weights for that. So hold on to the next part of the lecture, and we'll talk a little bit about that.